I want to talk about the convergence results, okay, just to convince you that this perceptron algorithm actually converges when the data set is intrinsically linearly separable. I'm not going to go into the proof because that would be extremely boring, okay, and then it's not useful anyway. But I want to mention at least what are the conditions that you need to satisfy in order for your algorithm to converge. So the theorem is stated as follows. You need to assume a few things. That the first thing is the two classes, they are linearly separable. That's the basic requirement. If they're linearly not separable, we have already seen examples that it's going to fail. So that's the first criteria. The second criteria is a very technical criteria, which you have absolutely no reason to believe that this is true, okay? It's just a bunch of equations here. Your y, and then you have this linear classifier is bigger than some gamma for gamma bigger than 0. So we will keep it as it is, okay? We will look at this later on. And then the third condition is that your data points, they are somewhat bounded, okay? So that you cannot have a data point that lives in positive infinity or negative infinity. You don't have a data point that's unbounded, okay? So that is the bound. And then you initialize your theta 0 equals to 0. Okay, so these are the 4 criteria that you need. If you can meet all these 4 criteria, then the batch mode perceptron algorithm converges to the true solution theta star, meaning this norm will go to 0 when the number of iterations exceeds this quantity. If you look at this quantity, it says everything about what you want. Here is the true solution, so that will define the magnitude of your solution. R is the bound of your data point, and gamma is some magical number that you put there. So as long as you can quantify these 4 criteria, then you can quantify the minimum number of iterations. As long as your number of iterations beyond this, then you will converge. No matter how big your step size is. Okay, your step size can be anything, but then eventually you will get there. So what are the meanings of these criteria? Let's look at the second one. This is the most technical one, okay? So what is the meaning of this thing? You have the theta star transpose your data point, okay? And then you have this yj multiplied with this thing is bigger than gamma j. This criteria actually comes out from the fact that your 2 classes, they are linearly separable. Now, why do I mean that? You have this yj here, and then you have this linear term. This is actually measuring the distance from a point to a line. Now, you trace back a few lectures when we discussed the separated hyperplane. That theorem, we mentioned that it's a very simple geometry between a point and a plane. That is measured according to your distance. You just put your data point onto your discriminant function, evaluate that will give you the margin. Okay? Now you put a yj here, and yj is just a +1 or -1. Okay, so if you have misclassification, you will have a value, right? So this yj is not too important. You just take care of the sign. But then you say that the distance between a point and a line is bigger than gamma. That says it is a linearly separable, right? Because if you have this criteria satisfied, then the 2 classes has to be linearly separable. So this is one criteria. Okay, so gamma is the margin, theta star is one solution that the margin is at least gamma. So you need that. How about the second criteria? Well, the second criteria is that you will want this theta 0 equals to 0. Okay, so if you don't start with 0, you can still get convergence, but then you just don't have a unique minimizer. Okay, and if you don't have a minimizer, then you don't know where you're converging to. Okay, because you want to prove convergence, you want to make sure that theta k converges to theta star. If you don't even know where you start with, you don't know. You just don't have a way to tell you what is theta star. So you need to start with a 0, so then you can quantify the convergence. Okay, so and then we talk about the batch mode. Okay, so the batch mode algorithm says that it will converge to this iteration. So that means you're constructing a sequence of theta case. Okay, so I'm writing here. So theta 1, theta 2, all the way to theta infinity. So you're showing that this sequence has a limit object. This limiting object is theta star. And then the number of iterations k is bigger than this quantity. And so what is the meaning of this k? Well, it will be at the next page. So it says that k will be bigger than this ratio. So if you have a big R, R is like controlling the radius of the class. So if you have a big R, then they're widespread, and so it's a little bit more difficult to construct. And so you need a larger k, and then gamma controls the margin. So if the margin is small, okay, if you have a very narrow margin, then it's a harder problem. Then of course you need to run more perceptron iterations to get to the right decision boundary. Okay, otherwise if it's big, then you need a small k. All right, so okay, so that is the like a 2-page summary of the perceptron convergence theorem. Okay, I'm not going to give you the proof. The proof is in the appendix. This is a summary of the convergence theorem. The algorithm that you use is gradient descent. You need to make sure you know. Okay, it's running on the soft loss, and then the solution you're actually getting a global minimizer for the hard case. That's the beauty. Okay. The main assumption that you're making is that it is linearly separable, among other technical assumptions, and then there's a margin that you need to worry about. Now, let me also comment on that this perceptron algorithm is good to know, but it may not be that useful in practice given all these deep neural networks nowadays. Okay, but knowing this perceptron algorithm, that gives you like a tool to analyze a lot of complicated problems. It's a very simple toy problem. And therefore, the algorithm is also very simple. If you know how to analyze this one, you can perhaps analyze a few more difficult problems. So that is the benefit of understanding the perceptron algorithm. Now, the reading list of this lecture is coming from here. In particular, I want to draw your attention to this chapter 1.2 and also 5.5 of these two books. They have a lot of details talking about these convergence, proof, algorithms, and so on. Okay. All right, so appendix will have the proof, and then I will see you guys next lecture.